Okay, Bergson and the Holographic Theory of Mind. Part 45b, A Quantum of a Crisis, Part B. We'll be looking at Bell's theorem, inequalities, hidden variables, what does this really mean, and Bohm's pilot wave, and how this relates to Bell, and hidden variables, etc. We'll get to the point that relativistic locality has to go, along with special relativity, and yes, there's implications. Did I mention the ether, which Bell advocated we return to. So we'll be turning to realism, not to the quantum weirdness or woo. In Part A on measurement, this is what we saw. According to the orthodox interpretation of quantum mechanics, Copenhagen, the theory provides, already with the wave functions alone, complete descriptions of physical states. But we saw multiple distinct and interrelated problems that afflict this view, at least according to people like Einstein, Schrödinger, and Bell. The wave functions provide only an incomplete description of what is actually going on physically. They fail to provide any comprehensible description of physically real processes at all, that is, the ontology problem. The nature of measurement, that is, the collapse, is utterly vague. And QM entails nonsensical situations, the dead and the live cat. And QM requires non-local, faster-than-light interactions. But how this works, a total mystery, especially to QM. Again, my main source, Travis Norson, his book, 2017. And my source for Norson was Adam Becker, who noted that in Norson's book is the actual and only true explication of Bell's theorem. We're going to look now at Bohm and the pilot wave, Bell and his theorem, and hidden variables. Starting with Bell. We saw the nature of hidden variables in Part A, seemingly inexplicable correlations that can be explained with just a bit of knowledge. Bertolin socks, in Bell's analogy. But we know this is how Bertolin is wired. That is, we see he's got a blue sock. We know the other must be red. But this is from Bertolin and his mindset. Two particles with opposite spin, but we know that this was their state in a molecule, now dissolved. So, warning here, these are local hidden variables. There are non-local hidden variables, non-local being faster than light interaction. This distinction will be all important. Keep it in mind down the line. Von Neumann, in 1932, had given a proof that no QM theory can employ any form of hidden variables. Bell says he knew of this proof via Born and accepted it, but he had been unable to actually read it because it was in German. What caused him to question it? Bell ran across Bohm's theory, 1952. There he saw a theory that did exactly what von Neumann said could not be done. That is, a very solid theory that used hidden variables. To quote, but in 1952 I saw the impossible done. It was in papers by David Bohm. Bohm showed explicitly how parameters could be indeed introduced into non-relativistic wave mechanics with the help of which the indeterministic description could be transformed into a deterministic one. More importantly, in my opinion, the subjectivity of the orthodox version, the necessary reference to the observer, could be eliminated. In other words, the mysterious collapse postulate with its reliance on observation, friends, measurement, gone. Noting the word indeterministic description versus determinism, it is the collapse that introduces the indeterminism into QM, because no one knows what's happening until we look. The dice, therefore, that Einstein detested. This could cause, or would cause, Bell to re-examine the nature and subject of hidden variables and von Neumann. And this must take us back to EPR, the Einstein-Podolsky-Rosen paper of 1935. Bohm, in 1951, we saw in Part A, did a recast of EPR. Consider a pair of atoms very far apart. each with a spin 1/2, say, one in Paris, one in Tokyo. You measure the z component of particle 1, you know 2's z component. They are perfectly anti-correlated. For locality, measuring the z spin of 1 should not affect 2's if they're that far apart. So per EPR, particle 2 must already possess a definite spin value, maybe from the now dissolved molecule that they both came from originally, the hidden variable. Else, 2 spin somehow comes into existence instantly, crystallizing out of a fog, that is, out of the quantum woo, with measurement. But this crystallization is equal to a violation of locality. EPR's claim to avoid non-locality, you must have predetermined values. We can also consider the x-axis, and the EPR claim is we require already definite values on both the z and x axes. Else, again, we have non-locality. And there's a little equation for the x-axis, again, antisymmetric, plus x minus x plus x. So locality requires a hidden variable theory of the type shown in this table. So we see particle 1, particle 2 in the two columns, and we see the z and x axis values. So the first row there, first pair type, particle 1 has a plus spin on both the z and x axes, so then particle 2 is forced to have minus spins on both axes, z and x. And then, of course, we have all the possible combinations. Second pairing, particle 1 has a plus spin on the z, minus 1 on the x, therefore you have to have the opposite for particle 2, minus 1 and plus 1, etc. So we see the psi equation is incomplete about each pair of particles equals one of the 4 subtypes, that is, one of the rows. Which of the 4 types a given pair of particles ends up as, this is random, with equal 25% probabilities for each of the 4 types, because the whole enchilada has to add to 1. Now, the quantum statistics could be read off from psi's rewritten in this form. So we get the whole enchilada all expressed there at once. So this sort of hidden variable model, particles with predetermined values for spin measurements along the x and z directions, this type of model can reproduce the quantum predictions but without the non-locality associated with ordinary quantum theory's collapse postulate. This is where things stood for decades. EPR in 1935 having shown this is a sort of hidden variable theory needed to account for the quantum mechanics correlations in a local way. Physicists ignoring EPR, believing Bohr had refuted EPR, that is, you can't measure both position and momentum at the same time. Podolsky having sort of screwed up and used an example that required both position and momentum, which was irrelevant. Notice in this particular little table, there's nothing here involving position or momentum. We're just looking at 2 different spin values. Enter Bell, 1960s. Could the local hidden variable model continue to reproduce the quantum mechanical predictions in a more general setting, where spin measurement along more indifferent axes are also allowed? We allow the experimenter on each side to choose among 3 possible axes, axes A, B, and C. Again, the singlet state can be written as such. We're looking at the A axis and the force antisymmetry plus A minus A in each case. Equally so, then, you could write the equation for B and C. Again, the outcomes will be perfectly anti-correlated, and a hidden variable table will again look like this. Now we have 8 possible cases. Again, we have particle 1, particle 2, and in the first row, first pair type, we see particle 1 has a plus spin on all three axes A, B, and C, so particle 2 is forced by antisymmetric to be -1 in all three cases. Second row, we've got a +1 for particle 1 on A and B, but a -1 on C. So we have the inverse case for particle 2, both -1 on A and B and a +1 on C, etc., all the way down the line. Now the frequencies we're leaving unspecified. The hope is to pick them so hidden variable theory is in accord with quantum mechanics, that is, quantum mechanics predictions. That is, by frequency is meant how often are these pair types events observed. That's what we're looking for. We want that frequency of observation to match what quantum mechanics would predict. But it's impossible. The proof is Bell's theorem. It shows that the frequencies, how often we see these events, are constrained by a certain inequality relation, but the quantum mechanical predictions do not respect this constraint. They show different amounts of time you'd see these, different frequency of observation. So no matter how the frequencies f sub I are selected, there are cases where the hidden variable theory cannot produce the QM results. Say we measure particle 1 on direction A and particle 2 on direction B. When is it that both are spin up, that is, both are plus? Well, we can just scan the table. I see this in rows 3 and 5. Row 3, I see particle 1 is a +1 on A, and particle 2 is a +1 on B. Got one. And again, pair type 5, particle 1 is a +1 on A, and particle 2 is a +1 on B. So we can write a little probability equation already. The probability of A, B, both being ++ is F3 and F5. Now there's two others. Take this case where we have B and C, probability of ++ on B and C. So in row 2 we see particle 1 has a +1 on B, and indeed particle 2 is a +1 on C. And another case of it, particle 1 is a +1 on B in row 6, and particle 2 is a +1 on C. So we have that little equation. Then we have yet a third case I won't show, but it's there, where we have 2 pluses on A and C for particle 1 and particle 2, respectively. So since all of the frequencies, the f sub I, must be positive and add to 1, we can already write an inequality. And it looks like this. The frequency of f2 plus f5 has to be less than, in other words, the number of times you observe f2 and f5 has to be less than the total of the frequencies or observations of f3, 5, 2, and 6. And this equally means we can write it in probability form. The probability of seeing a ++ in A and C it's got to be less than the probability of seeing a ++ in A and B and also on B and C. So a theory in which spin measurements simply reveal pre-existing values, hidden variables from that molecule up there, will have to make statistical predictions that obey this equation. Now we could go deeper with Norson into the math underlying the QM predictions, but we can neglect this. The form of experiment is this. Produce a bunch of spin 1/2 particle pairs. Have them fly off in opposite directions toward Stern-Gerlach measuring devices, which could be oriented along one of the three directions, A, B, or C. Then keep track. How often, when the A spin of particle 1 was measured and the B spin of particle 2 was measured, both measurements yielded the spin-up, the ++ outcome. That is, we would empirically measure the probability of A and B being ++. And similarly for the probability of a ++ on both the B and C directions for the particles, both particles, and then for the A and C on both particles. Then compare these probabilities to this equation. If Bell's inequality is respected, quantum mechanics is refuted. Hidden variable theory is vindicated. If QM's predictions are respected, then hidden variable theory, again local, is refuted. The first really systematic test of the Bell's inequality was done by Alan Aspect and his collaborators in 1982. Instead of using pairs of spin 1/2 particles in the spin singlet state, they used pairs of photons emitted from excited calcium atoms. Their polarizations are entangled in such a way that is perfectly analogous to the singlet state we've been discussing, where we're simply describing an equation with a spin on one axis. Their summary: our experiment yields the strongest violation of Bell's inequalities ever achieved, in excellent agreement with quantum mechanics, that is, with QM predictions. Since it is a straightforward transposition of the ideal Einstein-Podolsky-Rosen-Bohm scheme, and I'm going to note here, remember, it was Bohm, that's why they've got Bohm there, who removed Podolsky's confusion factor that allowed Bohr to obscure things, and recast EPR simply in terms of the spin 1/2 particles. So the experimental procedure is very simple and needs no auxiliary measurements, as in previous experiments with single channel polarizers. We are thus led to the rejection of realistic, that is, hidden variable local theories. So again, looking at our little schema up there, if Bell's inequality is respected, QM is refuted, hidden variable vindicated, but in this case, they saw this check mark on QM's predictions are respected, and hidden variable theory and something like then our hidden molecule is refuted. It has to go. Since then, there have been multiple experiments aimed at closing any possible loopholes. I note Kastrup, Stapp, and Kafatos in an article. These are there is no objective reality gang, citing a 2000 and a 2007 and a 2010 finding. Norson notes 3 in 2015. Here they are, all in 2015. But what does this really mean? So there have been a number of experiments which now show that no local hidden variable theory can be correct. Note local. This is obscured. The results are routinely interpreted to mean any or all and any hidden variable theories must be incorrect. This includes by implication Bohm, and this is wrong. Take Hawking, for example. Einstein's view is what would now be called a hidden variable theory, but these hidden variable theories are wrong. The British physicist John Bell devised an experimental test that would distinguish hidden variable theories. When the experiment was carried out carefully, the results were inconsistent with hidden variables. Thus it seems that even God is bound by the uncertainty principle. God does play dice with the universe. Now I'd note, and Bell insists on this also, determinism in dice is not the issue. It is locality or non-locality. Kind of a standard misconception on the issue. It's only the collapse that introduces the indeterminism into QM. One could give a plethora of such quotes. Why such a position when it is known that Bohm's theory, as we'll see, fits these findings? Some of this is indeed lack of knowledge of Bohm, but the prime reason for physicists, they do not want to give up relativistic locality, as they term it. Their choice, as they see it, uphold locality, that is relativity / SR, special relativity, and reject hidden variables, or uphold hidden variables and reject locality, which they equivalence with SR. Physics takes one, that is, keep special relativity / locality, even at the cost of abandoning a more complete QM model. That is at the cost of quantum Mysterianism, the collapse. Norson, that I think captures the viewpoint of the vast majority of physicists today, but I believe it is completely and utterly and hopelessly wrong. We do not face anything like the choice between options 1 and 2 above. And indeed, at the end of the day, Bell's theorem tells us absolutely nothing about hidden variables or determinism or counterfactual definiteness or realism or whether the moon is there or not when you aren't looking. To continue quoting, everybody is just simply wrong here because they have forgotten, or more commonly because they have never understood in the first place, a crucial part of the broader context of Bell's theorem. In particular, they have forgotten the EPR argument, which, remember, is supposed to be a proof that deterministic hidden variables are required in the first place precisely in order to avoid non-locality. Bell rules out a form of hidden variable theory, a form. This form is what EPR considered specifically. Why? This form is the only possible hope for maintaining locality in the face of the perfect EPR correlations. Bell's theorem, the proof that local hidden variable theories are wrong, local, must be understood as the second part of an overall two-part argument, the first part of which is the EPR argument. Schematically, EPR, locality implies X. Bell, X implies conflict with experiment, where X equals the local deterministic hidden variables. Obviously, if X is in conflict with experiment, we cannot maintain X, which means we cannot maintain locality, because locality entails X. The conclusion from these experiments, not that we cannot have hidden variables, we can, not that we must choose between locality and hidden variables. Rather, EPR implies keeping locality but abandoning hidden variables, but that's not an option. We must, that is, simply conclude that locality, that the prohibition on faster-than-light causation that seems somehow to be implied by relativity theory is false. Relativistic local causality is wrong, is in conflict with experimental data. Faster-than-light causal influences really exist in nature. This is not a choice between Einstein and Bohr. If it is not either or, but one will often see it put this way. The quote, Bell showed that Einstein was wrong, Bohr was right. You see a statement equivalent to this in these kinds of YouTube's Einstein's Nightmare, Illusion of Reality. But this is not the only option. Norson, quote, relativistic local causality is wrong. Now me too, are glimpsing the why of, say, my number 18 and number 22 on Tesla, the ether, fields, magnetism, 8A, 8B, 37, the non-ontological character of special relativity, its logical inability to explain any physical real effects. And number 17, on Bohm, my concern in that one that he had himself drunk the Kool-Aid with respect to special relativity. We'll continue on these implications after we see Bohm. So Bohm, the pilot wave. The theory was first proposed but then prematurely abandoned by de Broglie in the mid-1920s. It was then independently rediscovered and further developed by David Bohm in 1952. Bell, who championed this theory until his death, said, while the founding fathers apologized or agonized over the question particle or wave, de Broglie in 1925 proposed the obvious answer, particle and wave. De Broglie showed in detail how the motion of a particle passing through just one of two holes in a screen could be influenced by waves propagating through both holes, and so influenced that the particle does not go where the waves cancel out, but is attracted to where they cooperate. This idea seems to me so natural and simple to resolve the wave-particle dilemma in such a clear and ordinary way. He goes on, discouraged, de Broglie abandoned this picture for many years. He took it up again only when it was rediscovered and more systematically presented in 1952 by David Bohm. There is no need in this picture to divide the world into quantum and classical parts, as we saw in part A. So Bohm and the pilot wave, start thereof. There's a remarkable simplicity to the start. We need to know the dynamical laws obeyed by both the wave and the particle. So for the wave, this is the Schrödinger equation, psi, which we've seen. For the particle, we get a clue from de Broglie's relating the momentum of the particle to its wavelength, or the wave number k of the particle's associated wave. So this is the fundamental de Broglie equation with his insight that even a chunk of matter has a wavelength. The little blue box shows the definition, lambda, the wavelength, in terms of Planck's constant h over the momentum. I have a little sign there. Bergson was here because de Broglie actually gave Bergson credit for creating the mindset, the zeitgeist, for viewing the field of matter as wave-like, matter waves. So the wave number, k, is simply the number of waves per unit distance, as opposed to the number of waves per unit time. So that's the fundamental little equation where we've got the momentum of the particle as a function of Planck's constant and the wavelength, wave number. We just need to see the wave-like character of the particle. And of course, one asks, how do you understand this particular equation unless the particle is both a particle and a wave? So when psi is a plane wave with a definite wave number, k, waves per unit distance, the particle moves with velocity, and here's our velocity equation, which is, again, just a function of the equation on the top, with the wave number k there, momentum, etc. So to generalize, when psi is not a plane wave, how do we generalize it with no well-defined wave number k? Well, we're going to skip a bunch of mathematical steps here, but we end with this kind of equation, showing the change of position with respect to time. And over on the right, we see the psi there and the momentum, etc., from the original equations above. This is basically it. A single electron is a wave and a particle. The wave is just obeying Schrödinger's equation. The particle is moving under the influence of the wave according to this particular equation. There is another aspect, and this is how probabilities arise in this theory. Norson explains this, but we'll neglect the math. But note the role of probability in the pilot wave theory. We'll note it. Every particle is always definitely somewhere in the pilot wave theory, but we don't usually know the exact location in our little particle in the box, which is a question mark. We experimentally prepare an electron to have a wave function psi at some position x at time 0, the start thereof of things. We cannot pick or control the exact initial particle position x at time 0. This, therefore, will be random. Thus, there should be some associated probability distribution, probability of x at time 0, to characterize this. Pardon my poor probability distribution picture there, but that's fundamentally what's going on. We have a probability distribution for the position x at time 0 for our particle. And no much math is being skipped here. I mean, there's a lot of impressive math, but I'm just boiling it down. And yes, it varies in time in such a way that if the probability of the position x at time 0 is equal to the psi function of x at time 0 squared, that is, this we call the square of the amplitude in the Copenhagen world at initial time 0, then we'll have the probability of position x, particle being there at time t, equal to the psi equation x at time t squared for all times. Note, this is the Bohm rule for probabilities. It's just dropped out. And this is what is termed equivariant in accord with Schrödinger. So one of the theory's main virtues, something like the Bohm rule, can be genuinely derived from the dynamical postulates of the theory, not merely posited, as in Copenhagen, as an additional axiom, the Bohm. For Norson, we can look at this as, at some cosmological initial time, t equals 0, the wave function was psi 0, and the particle positions were selected randomly according to the psi squared distribution at that initial time. It then follows from the two dynamical postulates of the theory that we, today, inside the universe, should see particle positions that are distributed according to the Bohm rule. Probability of x at t is a function of the absolute value of psi at x at t squared. Going back to the particle in a box, for some non-trivial dynamics, we start with a superposition of energy states, or energy eigenstates. The wave intensity sloshes back and forth within the box. So here on the right side we have a space-time diagram. The position of particle x equals 0 to x equal L along the horizontal, the particle moving along the box, and over time moving along in the vertical. The distribution becomes very non-constant. You can see several trajectories are bunching closely together after a short period of time. But in this, the main ideas of the pilot wave theory. A quantum system is a hybrid of particle and wave. The wave, the usual wave function obeying Schrödinger's equation. The particle has a random initial position within the wave, as we saw last slide. Then this position then evolves in time according to the guidance equation, which we're looking at the bottom there. So the motion of the particle is well captured by Bell's statement. The particle is attracted to where the contributions to psi cooperate. That is where there is constructive interference. That is where psi squared is large. So at time 0, psi squared is large on the left side of the box. The little red distribution there, the little red lines are showing that, and then small on the right. But after a short period of time, psi squared becomes small on the left and large at the right. And the little green lines are showing the position of the particle. The particles thus move from left to right to follow the square of psi. To visualize the possible particle trajectories in the case of two-slit interference, beginning with a superposition of two Gaussian, that is, probability distributed wave packets. You're sent at x equal a and x equal minus a, which is there in the equation. One can see the a and minus a. But that's the equation for the movement. And as Norson puts it, there's no way to solve this, I say, by numerically through a computer. And so this pretty much is what it looks like when you display it. So here you have the trajectories of the particles emerging from the slits. It's again a form of space-time diagram. Time moving to the right, and the positions of the particles moving along the vertical. So the highly non-classical motion of the particles is influenced by the accompanying pilot wave. The particle trajectories bunch up around points of constructive interference. Again, an ensemble of such trajectories with suitably random initial conditions perfectly account for the type of statistical interference pattern seen in the two-slit interference case, and for Bell in a clear and ordinary way, as we saw in previous quote. Which is to say, so much for the double-slit quantum woo. So we've assumed if we make a position measurement at some time t, when the wave function is psi x of t, so that is psi at some point x over at some point time t, and the actual particle position is x at t, we will see the particle where it is. For a particle following one of the trajectories, we see a flash on the detection screen right where the particle hits it. But the most important virtue of the pilot wave theory, no need to divide up the world into quantum system, which we describe via the theory, and classical environment. No need to introduce what Bell called a shifty split, an artificial division of the world into distinct quantum and classical realms, with special ad hoc exceptions, that is, the Bohm rule, to the usual dynamical rules when the two realms interact. The claim, unlike orthodox mechanics, the pilot wave theory is not afflicted with a measurement problem. Take the particle in the box and the measurement pointer, where we treated them as one system before. And of course, we saw all the superposition problems. With a single energy state for the particle, everything is fine. The pointer has a definite value per Schrödinger and psi. The problem, if the particle starts in a superposition of energy states, like we're showing actually in the box there with our two states, psi 1, psi 2, the linearity of psi now blurs everything. Again, a little equation where you have the sum or pile of possible energy states and the pointer value being multiplied by this. And so the pointer is infected, as we saw in part A, with the quantum ambiguity. The interaction between the particle in the box and the pointer infects the pointer with its quantum ambiguity. That is, the final state is a superposition of terms like the particles in the ground state and the pointer indicates the energy state is equal E1, and the particles in the first excited state and the pointer indicates energy state is equal to E2, and so on. The wave function alone fails to pick out a particular result. Instead, it contains, so to speak, all possible results in parallel. How does the pilot wave theory resolve the problem? For the theory also says there is a wave function which obeys Schrödinger's equation. For pilot wave theory, the wave function alone does not provide a complete description of the physical situation. Crucial here, there is in addition the actual position x of t of the particle and the actual position y of t of the pointer. So this little picture here is how psi x, the position x of the particle, y, the value of the pointer, evolves with t in time. As time goes on, the superposed terms in psi move in the y direction by different amounts, and after a while, psi has support in a set of discrete, non-overlapping islands, as we see on the left of the configuration space. But the particles have definite positions, x of t and y of t, and together can be understood as an actual configuration point, which traces out some kind of trajectory through configuration space. So again, we've got a possible start and a possible end, precise point of the trajectory of the particle, which corresponds with y, of course. The exact trajectory is twisted and complicated. The several wave function islands move from their initial stacked configuration to their final separated configuration, sliding across one another. There's a complicated interference pattern. The simultaneous presence of all of these islands constitutes, for orthodox quantum mechanics, the measurement problem. The indicated y of t is in support of the n equal 2 branch of the wave function, in the middle where we're pointing there. That is, y of t is approximately, well, the little term there, a function of the energy value 2 time. So we would say, in this case, that the energy measurement had the outcome E equals E sub 2. At the end, the pointer position is in no way blurry. It has a definite position. This position corresponds to one of the energy values. So particle, pointer is all being treated as one system in pilot wave theory. Pilot wave theory generates the same statistical predictions as ordinary QM, even though the theory is completely deterministic. And Schrödinger's psi evolution is deterministic. It's the collapse, that is the postulate, that introduces the indeterminism, randomness, QM statistical nature, as we've been noting. In the pilot wave theory, there is no collapse postulate. The wave function obeys the Schrödinger equation always. And the dynamics describing the motion of the particles is also completely deterministic. Randomness enters only through the initial conditions, which we can never precisely specify in the first place. Yes, this is where the uncertainty principle enters, in the initial conditions, but this principle reflects a limit on our knowledge, not a feature of reality. So assume so far, position measurements simply reveal the pre-existing positions of the particles. The analogous thing does not appear to hold in the case of energy measurement, though. Now we're talking the subject contextuality. Yes, the measurement of the particle in the box, the PIB energy, had a definite outcome, E of n. We saw E2. This in no way implied that the particle somehow secretly had this particular amount of energy prior to the measurement interaction. Better, the particle doesn't really have any particular energy prior to the measurement. It does have one after the measurement. For measurable quantities other than position in pilot wave theory, measurements for the pilot wave theory do not just passively reveal the pre-existing value of the quantity in question. This is partly what is meant by saying that for the pilot wave theory, properties like momentum and energy and spin are contextual. This goes a little deeper. It's not that the pre-measurement value and the result of a measurement of a certain property can in general be different. Rather, there may be no such meaningful thing as the pre-measurement value of that property at all. Yes, pilot wave theory is deterministic, but the measured outcome always depends on the details, on the specific method of the measurement. Different and perfectly equally legitimate methods of measuring the energy of the particle in the box will yield different measurement outcomes. So what a theory says about measurement should be extracted from rather than awkwardly tacked on or appended to the theory's fundamental dynamical postulates. It's not the case. In pilot wave theory, some pre-existing energy value is revealed by, or even somehow affected by, and then revealed by the measurement procedure. For Bell, the word measurement comes loaded with meaning from everyday life, meaning which is entirely inappropriate to the quantum context. When it is said that something is measured, it is difficult not to think of the result as referring to some pre-existing property of the object in question. When one forgets the role of the apparatus, as the word measurement makes all too likely, one despairs of ordinary logic, hence quantum woo, or quantum logic, in other words, woo. When one remembers the role of the apparatus, ordinary logic is just fine. I note, even Einstein showed that measuring our poor toaster, measuring length, is going to be a function or contextual if your measuring apparatus turns out to be clocks and light rays. That is, if you choose that measuring procedure, well, the length of the toaster is going to vary, unfortunately. But in any case, this is important. This allows us to understand how it is possible for the pilot wave theory to exist and work in the face of the no hidden variables theorems. These invariably apply only to non-contextual hidden variables. Measurement seems to imply pre-existing, not. So now we reach a curious problem. For context, here's Bell. But why then had Bohr not told me of this pilot wave, if only to point out what was wrong with it? Why did von Neumann not consider it, when even Pauli, Rosenfeld, and Heisenberg could produce no more devastating criticism of Bohm's version than to brand it as metaphysical and ideological? Why is the pilot wave picture ignored in textbooks? Should it not be taught, not as the only way, but as an antidote to the prevailing complacency, to show that vagueness, subjectivity, and indeterminism are not forced on us by experimental facts, but by deliberate theoretical choice? That is, the woo is being chosen. There is one feature of pilot wave theory that explains this reluctance. The pilot wave does not solve the locality problem. It makes it blatant. It is manifestly non-local in this sense. The velocity of each particle at a given instant depends on the instantaneous positions of all other particles, at least when there is entanglement. Now note, already here is a hint of the holographic in 1980. Remember Bergson's justification. Build up the universe with atoms. Each of them is subject to the action variable in quantity and quality according to the distance exerted on it by all material atoms. Ring and Faraday centers of force, the lines of force emitted in every direction from every center bring to bear upon each the whole, or the influence of the whole material world. So in this statement that we're depending on the instantaneous positions of all other particles, we're getting a prefiguring, so to speak, of Bohm 1980 in a holographic vision. For a two-particle system, the equation for the velocity of particle 1 is this expression we're looking at, nice and complicated. On the right-hand side, the position x1 depends on the position of particle at x2. That is, and 2 could be 1,000,000 miles away. The dependence is immediate, instantaneous. There is no velocity of light delay. Norsen describes an example. We measure the energy of particle 2 1,000,000 miles to the right. We cause a sudden and dramatic change in the behavior of particle 1 1,000,000 miles to the left. It goes from oscillating back and forth to just sitting there at rest. We make it stop moving instantaneously from 1,000,000 miles away. It's a truly blatant case of spooky action at a distance. It seems impossible to reconcile with the relativistic concept of locality, as it's always termed. That is, all causal influences propagate at or below the speed of light. But this is not transmitting a signal faster than c, the speed of light. Pilot wave theory does not allow or imply this. Bell identified the assumption of non-contextuality as a hidden ill in the hidden variable impossibility proofs. On studying Bohm, he had come to wonder if non-locality was a necessary feature for any hidden variable theory. The quote, however, it must be stressed that to the present writer's knowledge, there is no proof that any hidden variable account of quantum mechanics must have this extraordinary, that is, non-local character. It would therefore be interesting, perhaps, to pursue some further impossibility proofs, replacing the arbitrary axioms objected to above, namely non-contextuality, by some condition of locality or of separability of distant systems. And this is what he did. And so we return to where we left off, slide 16, that is EPR, keeping locality but abandoning hidden variables as not an option. We must, that is, simply conclude that locality, that the prohibition on faster than light causation that seems somehow to be implied by relativity theory is false. Relativistic local causality is wrong, is in conflict with experimental data. Faster than light causal influences really exist in nature. This was the position of Bell. Indeed, he went so far as to suggest the rejection of fundamental relativity and the return to a Lorentzian view in which there is a dynamically privileged, though probably empirically undetectable reference frame. To quote, it may well be that a relativistic version of quantum theory, while Lorentz invariant and local at the observational level, may be necessarily non-local and with a preferred frame, or ether, at that fundamental level. And, continuing, I would say the cheapest resolution is something like going back to relativity as it was before Einstein, when people like Lorentz and Poincaré thought there was an ether, a preferred frame of reference, to which I'd add Tesla, Steinmetz, Alexanderson, Heaviside, Maxwell, Thomson, Whittaker, all the heavies of electromagnetism based in the ether. But that our measuring instruments were distorted by motion in such a way that we could not detect motion through the ether. Now, in that way, you can imagine that there is a preferred frame of reference. And in this preferred frame of reference, things do go faster than light. Behind the apparent Lorentz invariance of the phenomena, there is a deeper level which is not Lorentz invariant. To quote, this pre-Einstein position of Lorentz and Poincaré, Lamore and Fitzgerald was perfectly coherent and not inconsistent with relativity theory. The idea that there is an ether, that these Fitzgerald contractions and Lamore time dilations occur, and that as a result the instruments do not detect motion through the ether, that is a perfectly coherent point of view. So Norsen, why did Bell take so seriously these sorts of ideas, which everybody else today regards as completely outmoded and wrong? Because he thinks his theorem and the associated experimental evidence proves that non-locality is a fact of nature rather than merely a defect of a type of theory we shouldn't believe in. So we are back to the true nature of relativity. Norsen, speaking of the difficulty of ditching relativity, to quote, relativity, one of the most successful and highly confirmed theories in the history of science. But this is BS. It is the unbelievable Jedi mind trick succumbed to now apparently by all physicists. This is Wiki's description of Fitzgerald's suggestion. Fitzgerald is better known for his conjecture in a short letter to the editor of Science titled the ether and the Earth's atmosphere, 1889, that if all moving objects were foreshortened in the direction of their motion, it would account for the curious null results of the Michelson-Morley experiment. So Michelson-Morley, as pictured up there, we have the Earth plowing through the ether current, or plowing through the ether concomitantly, then an ether current flowing past the Earth. And the apparatus is oriented such that one beam is directed crosswise to the current, one in the same direction as the current. And the little Pythagorean math shows you that there's going to be a longer swim time for the current flowing, or the light beam flowing down the pipe in the direction of the current and then back again, than for the light beam swimming crosswise to the current. So one would expect then that the two beams are out of sync and there's an interference pattern. And the null result was that there was no interference pattern. And what they're saying is, Fitzgerald said, well, we can fix that by admitting that since we're plowing through the ether, that arm in the direction of the current is foreshortened or shortened up a little bit, just enough to compensate for the longer swim time. Therefore, the two light rays will have equal travel time and there'll be no interference pattern. Fitzgerald based this idea in part on the way electromagnetic forces were known to be affected by motion. In particular, Fitzgerald used some equations that had been derived a short time before by his friend, the electrical engineer Oliver Heaviside. The Dutch physicist Hendrik Lorentz hit on a very similar idea in 1892 and developed it more fully into Lorentz transformations in connection with this theory of electrons. So here thus far, the length contraction is indeed physically real. It is based in Maxwell, Heaviside, electromagnetism, in turn, as these guys thought, based in the fixed frame of the ether. Relative. Only in this sense, an object must be in motion through the ether. Bohmian continues. The Lorentz-Fitzgerald contraction, or the Fitzgerald-Lorentz contraction hypothesis, became an essential part of the special theory of relativity. Now, how they did that is an interesting question. As Albert Einstein published it in 1905, he demonstrated the kinematic nature of this effect by deriving it from the principle of relativity and the constancy of the speed of light. But this is a no. Einstein erased the actual physically real length contraction based in the ether and electromagnetism and Oliver Heaviside and everyone else involved. He embedded the Lorentz equations in a system of observers reciprocally at rest or in motion. Observer 1 at rest, observer 2 in motion, or observer 2 at rest, observer 1 in motion, reciprocal. The ether became irrelevant in this. Nothing about the ether whatsoever, nowhere in the picture. The length contraction and the reciprocal time dilation, because in the Lorentz equations, length compensates for time, and vice versa, became purely measurement effects, divorced from the ether. Like measuring a toaster, like I like to say, with two different rulers. Same ruler, one says 5 inches, one says 9 inches. The toaster is not expanding or contracting. It's a measurement effect. But SR rulers are light rays and clocks, synchronized or not, same difference. No actual expansion or contraction of the apparatus arm or the toaster. Again, the ether in the system, irrelevant, removed from the ether, the length. So the strange contraction that physics did not like was gone. All is explained via special relativity as measurement effects. And everyone was happy. Then, undeniable physical clock slowings in jets, for example, were found, and longer living muons when traveling at high velocity, and not to mention the twin paradox, where the twin on the Earth ages more rapidly than the twin on the rocket. Now what to do with these? Respecting special relativity's intrinsic reciprocity of observers became absurd. Why? Because the Earth could be considered moving away from the rocket's stationary. Now the effect switches. Even Einstein admitted this. Or the plane carrying the clock lands at the airport. Its It slowed, but there was a clock on at the airport. And you don't see observers on the airport coming forth and saying, well, it was actually us that was moving around on the Earth around you, the plane being stationary, or the jet was stationary, the globe circling underneath it. No one claims that, because it's absurd. So what happened? Special relativity was simply contorted to explain these time slowings. It was simply used, appropriated to explain them as ontological, as physical, as real, as not merely measurement effects. These are real effects. The time is really slowing. The clock is really slowing while it's in motion around the Earth. The muon is actually living a bit longer as it plows through the ether. So by explaining these effects, SR thus became one of the most highly confirmed theories. And everyone's happy again. But this is a logical absurdity. In SR's system, the effects are reciprocal. Time units expand in proportions lengths contract. This is the elementary mathematical reciprocity in special relativity. So you've got two reciprocities, that of the observers and the mathematical reciprocity of the effects. So the effects must be of the same order, and this is measurement. But meanwhile, the Michelson-Morley arm length contraction is held to be purely measurement to protect physics' non-ether Michelson and Morley quote-unquote explanation. To show you how absurd this is, take the pole-barn paradox, driving this absurd state of physics home. This paradox, quote-unquote, is used as a veritable physics parable to show that special relativity's length changes are not ontological or real. At rest, the pole is too long to fit inside the barn, but at high velocity, moving through the barn, suddenly it fits in the barn. But, says physics, here, in this case, remember the reciprocity of observers. Put the barn in motion. Now the pole does not fit because the barn is contracting. So length changes are not real or ontological. See? This is, again, BS. Ignoring this dependence of logic with respect to time changes. As I said in 8a, physics could arrange an analogous experiment to prove the pole indeed fits or shortens and fits inside the barn or some analogous form of apparatus. But then, again, what would happen to the Michelson-Morley explanation? The reality of physics has no theory of the contraction or the time dilations other than Fitzgerald's and Lamore's, these being based in the ether. So SR is utterly not ontological. It describes measurement effects, period. It cannot be used to explain real physical effects. It cannot be used to explain slowing clocks, longer living muons, or a slowly aging twin. Its relativation of simultaneity has no physical ontological status. This is not a feature of the transforming universal field. SR is currently contorted as an absurd, inconsistent mess. The Michelson-Morley apparatus arm is merely a measurement effect, a non-ontological, a not really happening change according to physics. But those slowed clocks, very real, very physical, ontological effects. We can explain those with special relativity. So SR in its logically consistent form has never been confirmed. There is nothing in SR that can be confirmed. The block to dropping special relativity is non-existent. And the Fitzgerald contraction, the Lamore dilation are not relativistic effects, other than the pure fact that you're in motion through the ether. Drop this confusing phrase. All of this was the argument between Bergson and Einstein, utterly missed nowhere in this book. Does zero justice to this argument, trying to straighten out the mess. Bergson's duration and simultaneity. Just a note. So we return to that strange dependency on particle 1's position on particles 2 a million miles away. Remembering Bell's quote, there must be a non-local and preferred frame or ether at the fundamental level. In this context, we call Bergson's statement, quote, though we are free to attribute rest or motion to any material point taken by itself, it is nonetheless true that the aspect of the material universe changes, that the internal configuration of every real system varies, and that here we have no longer the choice between mobility and rest. movement, whatever its inner nature, becomes an indisputable reality, we may not be able to say what parts of the whole are in motion, acknowledging relativity in a sense. Motion there is in the whole nonetheless. In other words, there must be real motion. Stars explode, roses bloom, trees grow, orchestras play. These are simultaneities. The parts of these motions cannot be relativized. Simultaneity is intrinsically part of the motion of the whole. It does not matter what is the state of motion of observers. These organic motions cannot be relativized. So continuing, of what object externally perceived can be said that it moves? Of what other that it remains motionless? To put such a question is to admit the discontinuity established by common sense between objects, quote unquote, independent of each other, having each its individuality, comparable to kinds of persons, is a valid distinction. Now this is saying there's no true distinction between objects, it's a apparent distinction. And on the contrary hypothesis, the question would no longer be how are produced in given parts of matter changes of position, but how is affected in the whole a change of aspect. He compared this motion to that of a kaleidoscope. Within the global motion of this whole, the motions of objects now become changes or transferences of state, like waves. In such a global motion, there is clearly simultaneity as well. So one could ask, is not the universal field and its transformation as organic as the rose, the tree? These considerations, in my opinion, are where we start on the implications of Bohm. So yes, to make sense of Bohm, as Bell argues, we need to return to the ether to actually understand it. And this equally means back to electromagnetism, a science suppressed, as Dollard argued, as we saw in 18, with the emergence of special relativity and QM. We discussed de Broglie's pilot wave double-slit solution in number 22, which relies, as he said, on a wave in the subquantic medium, which we suspect would be the ether. It was hard to avoid that he was assuming something like the ether. It would seem that that whole transforming is the ether. So curiously, what is that photon being emitted in a double slit? Tesla, not even liking Maxwell, thought light was analogized to sound. It is like a longitudinal wave, compressions and rarefactions of a medium. The speed is a function of the density and permittivity of the ether. Point being, if light is a perturbation of the ether, just as there are no sonic tones, like photons, sonic tones being emitted from a violin, no thing is being emitted from the light source. No bullet, no photon, understood as a tiny bullet. Starting from these thoughts, Bohm could begin to make more sense. So Norsen sees only two worthy alternatives to Bohm: Everett's many worlds, GRW, or spontaneous collapse. As contrasting sharpenings to pilot wave theory, it's worth a peek. So let's start with Everett's many worlds. Now we saw pilot wave theory, the collapse postulate, get rid of it, and it was gotten rid of. For many worlds, the collapse postulate also, get rid of it. For many worlds, there is only the wave function, psi. That's what they want to stick to. So how does many worlds do this? How does it get rid of the collapse postulate, and does it really? Recall in treating the particle and the pointer as a single system. Pointer and particle became an entangled superposition. Both became fuzzy-wuzzy, both a superposition of states. And the equation for both, after evolving for a time t, we saw on the right there the sum of a pile of particle states, ci, psi I, being multiplied together by the pointer phi and ending up as a superposition of states, entangled particle and pointer in multiple states. But now, why not say the observer is entangled? And then we have the equation, we throw in the observer. And so we end up with the observer as part of the multiple states. His mother calls. She gets entangled. We'd have a term for her. A bird sings, generates some airflow, gets entangled. Oh, we need a term for the bird. Yes, this entanglement will extend. We'll have terms for everything in the universe. We'd have one giant psi equation. Observer, mom, bird, all a pile of states, and all fuzzy. But this does not mean the observer sees a fuzzy pointer. The observer, just acts like the pointer. He acts just like the pointer. One of his states sees or tracks one of the pointers. So the right-hand side of that equation there, where the observer is now mixed in after the arrow, it's not an incomprehensible blur, not everything happening in a completely mixed up way. And remember, not just the observer, but the bird, mom, everything can ultimately have terms in that equation, the universe. So rather, definite correlations are built into the state. It's an orderly mixture in some sense of several individually perfectly reasonable situations. The particle has a definite energy. The pointer indicates correctly what its energy is. The observer sees the pointer indicating its energy and correctly and validly infers what its energy is. Thus, when previously we said one possibility of many paths is realized, for multiple many worlds, all possibilities are realized. We have all these threads going simultaneously. So the world splits, say on an interaction like the particle in the box with a pointer, in several branches or threads, each a realization. But this is not multiple universes, as it's often been dubbed in common lore, as though whole new copies of universes are being created instant by instant, each existing separately, like the picture tends to show. We have one universe with multiple existing patterns, threads going on within it, in an extremely high-dimensional configuration space. In fact, how high a dimensional configuration space? Well, take our pointer and particle in the box pointer interaction. The pointer would probably consist of 10 to the 23rd particles to be a nice macroscopic object. So the two psi packets, like in a little box there, don't just separate by a distance d, say 1 centimeter, but rather by d, the distance in 10 to the 23rd distinct coordinates. So 1 centimeter times the square root of 10 to the 23rd equals 2 million miles worth of separation. That is, those packets will never act again. You have massive separation of threads or worlds. The start of many, many problems. Note, we're throwing in the wastebasket there the collapse, but simultaneously then the Bohm rule, because the Bohm rule codifies the collapse. But the Bohm rule is the only thing that makes quantum mechanics useful. It gives the probabilities of observing what, where, for example, where a little particle will be, according to the wave equation. So many worlds must have something like the Bohm rule. The problem: take a particle with 50% chance of being spin up, which means also 50% chance of being spin down, equal amplitudes. So we'll call this heads tails. Now, per many worlds, it's not quite right to say we're looking for the particle spin up, because in many worlds, both heads tails will happen. The split occurs, right? So here we're having our little observer. He's about to throw lots of heads and tails. And the very first time he throws, well, he's going to split because both things happen, heads and tails. So now we do this test 4 times. we'll see a branching structure as shown there. Every time we throw, we get the heads and tails. Now, generally, in this structure, we're going to get the Born amplitudes equal heads and tails in paths through these worlds. For example, that little red line I've shown there is a tail heads, heads tails path. And there's a good number of these tail heads, heads tails paths. Of course, there's other paths that don't correspond to this. For example, we've got the all tails path, we've got the all heads path, we've got heads, tails, 3 heads, 1 tail, etc. But in general, we can argue if we do a statistical analysis on it that these other paths are going to be relatively rare, and we're going to get mostly the head tails type path, equal amplitude path of Born. So far, many worlds is okay, it gets a dispensation. But if the particle situations are not 50%, 50-50, in other words, we have unequal amplitudes, which is very easy to arrange, all this falls apart. Now many worlds must generate branch weights. It must weight each of those branches according to some proportions, etc., to look like quantum mechanical results. Again, they've got to equal those frequencies that QM predicts, like, as we talked about in hidden variables and Bell. But it turns out these weights are really derived from the same basis as Born's rule. And so this is a very disturbing circularity in the whole many worlds theory. We're not really getting Born's rule dropping out naturally. Now, Sabine Hossenfelder makes a correlated argument in the video, which I'll put in the description. Again, arguing that many worlds ends up with the measurement problem anyhow, as you've just sort of said. I think this is another interpretation of many worlds, which holds that we evaluate only one branch of the detector, because there's lots of different defenses and arguments surrounding this aspect of many worlds. And then finally, I'll just note, if you think many worlds doesn't have an ontology problem as well, well, think again, as Norson discusses this. Just because we have the wave equation, if you remember, doesn't mean we get out of this difficulty. Remember how Schrödinger struggled to make the wave equation physically real, ontological. And many worlds really has the same problem. Then let's look at GRW after Girardi, Rimini, and Weber. The GRW, the collapse postulate, instead of get rid of it, it's make it more reasonable. Remove, lessen the mystery, smooth it out over time. That is, marry psi and the collapse. Transform collapse into something more palatable. Or another way to look at it, we're going to modify Schrödinger's equation with stochastic probabilistic terms, which preserving the evolution for microscopic systems and also ensuring that macroscopic things like pointers and cats end up in definite non-superimposed states. I know it's kind of curious. Bohm was already here. That is, this was considered his suggestion in 1966. So for GRW, the various psi should occasionally, randomly, spontaneously, naturally localize in position space around a position. So remembering our equation for motion, taken from the original Schrödinger equation, motion of a particle, single particle there, change the position x in time. We have the standard time evolution. The collapse postulate is transformed to this: a constant probability for unit time that a collapse will occur. There we have the probability, there the per unit time, change of time, and that's the constant. So that's going to be factored into this equation. And given GRW's value for this constant, the average time, we'll call it tau, between localizations is, tau is 1 over lambda there, it's equal to 3 times 10 to the 8th years. That's 300 million years between spontaneous localizations, that is, between collapses, between that point appearing somewhere and then again another place. Again, we're going to see this is roughly, that is, a rough localization. It's not entirely precise either. 300 million years. No way to test for a single particle with that. Again, another key parameter though, the length range for the localization, called sigma. It's roughly 10 to the 7th meters, so 10 to the minus 7th. So that sigma, roughly, if you have a psi distribution is fairly distributed there, then you're going to get the collapse of the localization, and it's going to be within that range, sigma, that the particle is going to be. So you've narrowed down the spot distance where the particle is going to appear. Again, that's why we're saying a rough localization. The implication here, if the particle is traveling through two slits and they're greater than sigma apart, which is normal for these slits, they're going to be much farther apart than 10 to the minus 7th meters. Should the particle collapse, it would then go through one slit and you'd see no interference pattern. This would seem highly testable, but again, you're going to fall asleep waiting for this for a few 100 million years. So not practical. But say your n for particles is 10 to the 23rd, and they're all entangled. Then if one particle localizes, all of them localize. And the wait time also goes from 300 million years to roughly 30 nanoseconds. So now you would have a constant barrage of localizations. The cat, the pointer, for practical purposes, are never seen in the superpositions Einstein and Schrödinger worried about. So this would also seem to solve the ontology problem, the charge density fuzziness, for example, that Schrödinger was so worried about, was trying to get rid of and never could, because, well, you don't tend to have this fuzziness at all. It's only fuzziness for a bit of time, which brings us to Bell's comment about GRW. For in GRW, he says, quote, the cat is not both dead and alive for more than a split second, which should cause you some concern, because this seems to be, in reality, kind of sliding over what is still a fundamental impossibility, fundamental nonsensicality. There's test implications. Seeing fuzziness yet at the 10 to the 23rd scale, this large scale, a pointer scale, etc., if you still saw that, GW would be disproven. This is the significance of the fuzziness seen still at the buckyball level, where n is 10 to the 3rd particles, so about 1,000 particles. So there's lots of orders of magnitude yet to go to get to the level where we're still seeing fuzziness, and GRW is then disproven. But physics is working towards this larger n to the 10 to the 23rd scale, thereabouts. But probably would take about 20 years at the rate that they're going. So talking of Copenhagen, Norsen, it is increasingly recognized as, in essence, what Slater pegged it as from the very beginning, a lot of vague and philosophical hand-waving intended to paper over the failure to explain things in the framework of space and time. In other words, physically. And on Bohm, in the pilot wave theory, Norsen, I have to agree with Bell's assessment that the pilot wave picture undoubtedly shows the best craftsmanship among the pictures we have considered. It is hard not to view the pilot wave theory as the most plausible and promising currently available option compared to the relatively contrived and ad hoc spontaneous collapse theories and the many-worlds theory and its sprawling difficulties with probability and ontology. And of course, there's ever the specter of special relativity. Its pilot waves apparent incompatibility with relativity is indeed troubling. However, Bell's theorem and the associated experiments seem to reveal that the pilot wave theory's non-locality is a reflection of a genuine feature of the world, rather than a disqualifying flaw. So we've seen the case for Bohm and the pilot wave, the escape route from the weird to quantum woo. The need to consider Bohm's pilot wave theory stands in the way of physics, seriously considering his other theory, I believe, his holographic model of the universe. And the holographic vision of the matter field with the brain as a reconstructive wave passing through it is precisely what Bergson relies on, with great academic reluctance of acceptance, because, well, there's no true holographic theory, and Bohm's theory really isn't considered. I would say see if you can find one philosophical discussion on Bergson that acknowledges his holographic aspect other than mine. I've never found one. Let me know if you find one. And thus an actual optical model of the origin of our image of the external world, that coffee cup being stirred, with the brain as a reconstructive wave passing through the holographic field. And thus a solution to the hard problem of consciousness, the origin of the image being the privileged aspect of this particular problem. Much is at stake till the above chain of events. And unfortunately, in the hands of physicists still confused on special relativity. I fear it's bleak for Bergson's elegant insight. I'm going to restate that last slide. Physics went off the rails with special relativity and the twin paradox. Bergson tried to head off the results in 1922. He was ignored. Physics went doubly off with quantum mechanics and the divorce of QM from the ether and the suppression simultaneously of the then advancing field of electromagnetism, and thus the big names, Tesla, Steinmetz, etc. All of this stands in the way of evaluating and understanding Bohm, thus of a holographic conception of the matter field, thus any actual understanding and acceptance of Bergson. Mix in the refusal of physics, psychology, and AI to examine their base metaphysic, the aura of absolute woo around AI and its conception of mind, Chalmers' misguided formulation of the consciousness problem, and plates and plates of crow to eat, the rejection of the ether, the ridicule of it, the exaltation of special relativity, plates of crow, to get an actual academic appreciation of Bergson's insight. We have a conceptual and social dynamic mountain of mud that's going to be extremely hard to move. So, next time we'll see. Until then, signing off.